Yes. So everyone is talking nowadays about C++ and security. So I thought I'd take a moment today to talk about our most treacherous adversary. No, it's not the nation-state sponsored hackers developing highly sophisticated exploits. No, it's not the ransomware groups recycling old unpatched vulnerabilities. We know those groups are trying to break our software, and they know it too. No, I'll tell you, our most treacherous adversary as C++ programmers is C++ compiler developers. Why are you laughing? No, this is a real tragedy. This is a sad thing. You see, we think they're our friends. If you've ever met them, they pretend like they're our friends. We think they're trying to help us, and they act like they're trying to help us. But really, the first moment we're not paying attention, they are totally prepared to turn on us and break our code. Recently, my team was working on upgrading one of our projects to use a newer compiler, Clang, and we got things building quite easily, and things looked good at first. But then we started observing some crashes inside of this function. Now, this function could not be any simpler. It takes a bool and it returns a string, true or false, and we have been running this code for years with no problems. But after upgrading to the new compiler, we discovered that we were segfaulting here with the stack all trashed. I will be honest, at first I thought we may have hit a compiler bug, because this is a really simple function, right? But as someone who's worked on compilers, I know that almost any time you think you found a bug in the compiler, it's not a bug in the compiler. So I started digging in, and I discovered that the compiler had made a fascinating optimization here. You see, the compiler needs to compute two things in order to construct the std string. It needs the pointer to the string to be copied, and it needs the length. And then it can use those to initialize the small string buffer inside of the std string with the appropriate text. So this code has a branch. It tests the value, and it does one thing if it's true, and it does a different thing if it's false. Now, if there's one thing that compiler engineers hate, it's branches. They know that if you can do something without a branch, that's way better. So compiler engineers love removing branches. So let's see if the compiler can turn this into branchless code. So first, it needs a pointer to the string. So we can load the address of the string true into RAX, and then we can load the address of the string false into RBX, and then we test the value, and we use this handy cmove instruction to conditionally select the right pointer based on the value. Cmove is a conditional operation, but it's not a branch, so that's kind of cool. So there's no problem here. But then we need the length, and here the compiler becomes just a little too clever. It says, aha, the value is a bool. It must be either false or true. It must be 0 or 1. Therefore, I can compute the length as 5 XOR value. Do you see it? If the value is true, or 1, then 5 XOR 1 clears the low order bit, and it gives us 4, which is the length of the string true. If the value is false, or 0, then 5 XOR 0 is 5, which is the length of the string false. So there's still no problem here. Unless, of course, the value has some other value that is neither false nor true, neither 0 nor 1, which can happen if you've accidentally left a variable uninitialized somewhere. So I looked at our crash dumps, and I traced this bool through about 20 layers of code until I found that, we had forgotten to initialize it. So, all right, that's on us, our mistake. So this code is wrong, right? Using the uninitialized bool results in undefined behavior, and so the compiler isn't technically wrong here. But it's a bit concerning, and as someone who works in security, this is the sort of thing that keeps me up at night. With the old compiler, this broken code worked, right? And yeah, maybe sometimes we picked the wrong string, but in this case, it turned out we were only printing the string to a log, so it wasn't a big deal. The new compiler, though, turns this formerly benign bug into a real runtime memory safety error that causes a crash. I mean, it was always a memory safety bug, but now it's no longer benign. In this case, the bug wasn't exploitable, but I could imagine all sorts of similar optimizations in this vein that might yield exploitable memory safety bugs. So yeah, my message to you is beware compiler developers, especially when they come bearing clever new optimizations. And okay, yes, always initialize your variables. And to finish with something serious, definitely do not use bool in any data structures that may cross privilege boundaries. That means do not use bool in any struct that may be saved directly to a file or transported over the network or pass between process boundaries and so on. Because a bad actor could write a bit pattern in that bool that is neither 0 nor 1, and then you might be in a lot of trouble. And it is not easy to write code to detect that you're in trouble, because the compiler may optimize your checks away, because it says, well, it's always true or false, 1 or 0, like, what are you doing? So maybe C had it right back in the days when bool types were just typedefs of int. And finally, always ensure that your slides are properly terminated.